Hello everybody, hope you guys are doing well. So continuing on our journey, today we will be starting with process synchronization. Um, First let's understand the need for process synchronization, and then we will see in detail about it. Okay, so just give me a bit. The process synchronization, basically you have multiples of process running, right? Either through threads or concurrently or in parallel. The threads often share user data, meanwhile, the operating system continuously updates various data structures to support multiple threads. A race condition. So, basically, why do we need this synchronization, right? So, basically, this is what can happen is since, so like, if I'm because we are doing concurrency, right? So, it can so happen that um, through threads are trying to access the same resource. So then this could lead into a race condition where we decide uh, which thread will act. So then this is nothing but a race condition is when access to shared data is not controlled, possibly resulting in corrupt data being sent. Process synchronization involves tools. So basically this is what we are going to achieve here. Now synchronization tools. Now cooperating processes that can affect okay so uh, So then, what's the solution, right? Okay, so this is nothing but mhm. And we already seen that process can execute concurrently in parallel. So you can have either you can perform parallel processing, right? So basically, parallel processing happens when you have multiple processors in use, right? So for example, this is one processor. Uh, this is another processor, and then you have one more processor, right? Parallel processing occurs when you have multiple processors are in use, right? Basically, this is basically you are having more than one processor, right? So you can run or you can schedule three different processes on three separate processors, right? So this is when you do parallel processing. So this is so when you're using server architectures or when you're using server motherboards, like those have parallel processing capabilities, right? Because you need to work on multiple requests, right? Now the other way is basically you have a single processor, but then you do something called as switching, right? So this is you have a single process. Then what you do is you give the CPU to different processes. The thing is, this happens so fast that we think that it's working uh, differently, right? But then it's working on a different processor. But then this is basically something called as switching, right? Or you do task switching. Then further down, you also nowadays modern computers you have a single processor, but then it can have multiple cores, right? So what you can do is, so instead of working on a single unit, what you do is you take so for example, you can have different processors, right? This is processor one, This is processor 2. No, basically this is a single processor, but then you're having different cores, right, on the processor. This is core 1, then this is core 2, right? So what you do is, so instead of running a single thread, you divide the program into different threads. Basically something called as multi-threading, right? And then what you do is you distribute these threads on the cores. So then this is nothing but what is multi-threading, right? Now we developed a model system operating so basically sequential or threading, all running asynchronously and possibly sharing data. Now we illustrate this model with a producer-consumer problem, right, which is represented paradigm. So there is a problem, right? Now we will return the consideration of a bounded buffer as we pointed out in the original solution. Suppose you want to modify an algorithm to remove. So for example, we are trying to modify a buffer, right? Now one possibility is to add an integer. Okay, let's see more. What's going to happen now? Uh, okay, so whenever you're accessing a buffer, basically the underlying you're going to go and work on the register itself, right? That's okay. That, what is the raise condition and how does occur? So producer, okay, you have uh, uh, now okay. Uh, so basically we return back to the size of a bounded buffer. As we pointed out, our original solution allowed as the most buffer minus one items in the buffer. Okay. So one possibility is to add an integer variable count initialized to 0. Count is no. What's the we will arrive. Okay, so this is basically how we are. Okay, suppose we have a code snippet, right? Okay, so this is a code snippet. Let's say this is while and then true, right? And then here we are doing count plus plus, right? And then we have a consumer, right, who is going to consume. So he's going to read data from here, right? So then it's going to be, so this is basically we have defined a buffer over here, and then this count is indicating that buffer size, and then when we are consuming we are going to keep on reducing, right? Although the producer and the consumer routines are correct separately, they may not function correctly when executed concurrently. So what if now we are talking about concurrency, right? So what if they both are working in tandem, like they both are working together? So what if in one I'm increasing the count and in one end I'm decreasing the count? So basically what could happen is as illustration, suppose is 5 and the producer and consumer process concurrently execute the statements. Following the execution of the statements, the value of the variable count may be 4, 5, 6. The only correct result though is count equal to 5, right? Which is generated correctly. The producer and the consumer execute separately. Now, inherently, what is trying to say is, although it might so happen that uh, it might be stored in a different register, right? So it could be a register 1 or a register 2 count. Even the register 1 and register may be physically same registers. Remember that the contents will be saved and also what is, so there is one more consideration that you might think, right? What if these are two So internally on the chip we are going to have registers, right? So these are basically two registers. This is going to be register 1 and then this is going to be my register 2, right? The concurrent execution of count plus version is equivalent to the sequential execution with lower level statements. Uh, here is one of the CPU similar the count. Now while again, even though register 1 and maybe same physical register, remember that the contents of this register may be saved and restored. Okay, so what is going to happen is the interrupt handler is going to do. Notice that we have arrived at the incorrect state count equal to 4, indicating that 4 buffers are full when in fact we have 5. Also, what it's doing is, yeah, first is count, then decrement. So, I mean, it could happen that since we are executing simultaneously, right? So before increment, we would perform decrement, right? That is also not correct, right? What if there is no value? What if this works faster? Or this is cool or scheduled faster on the core? So this is basically what leads to a condition called as rakes around, right? We need to avoid. So we need something called as synchronization that is to happen. We begin our consideration of process synchronization. So this is basically when we do this is nothing but called as the synchronization, or this is the reason why we need synchronization. Now there is a problem. There is something called as critical section, right? The critical section is again the same thing. I consider a system consisting of n processes. Now each process is called a critical section in which the process may be accessing and obtaining data that is shared with at least one process. The critical problem is to design a protocol and the process to synchronize their activities so as they cooperate with each other. Each process must require permission to enter its critical section. Okay, oh, now when we say we are this can happen, right? Race around can happen. So what if I have two processes? Now remember, whenever you create a process, so each process gets its own block, right? And even this is a different process. Both of them have their different code blocks and other things, right? So now what if I'm trying to access a resource which is common to both? Now there should be something, right, to avoid the race around. This is nothing but the critical problem. Basically, what we want to do is we want them to work in synchronization. That like they shouldn't be out of sync, right? We want them to work in tandem with each other so that we get the proper state. So for this we have designed certain rules, right? So there are three requirements or three principles that we follow. Basically, first is mutual exclusion. The mutual exclusion is says that if a process is executing, so this is basically um, how to resolve. So how to solve the critical section problem. So whenever we are into critical section, so whenever we are in critical section, so there are three major rules that we have to follow. First is basically mutual exclusion. That if a process P is executing its critical section, then no other process can execute in the critical section. The second is progress, right? If no process executing and some process wants to enter the critical, then only those processes that are not executing in the remainder sections can participate and decide which will enter. So then second is something called as progress, right? So mutual exclusion states there is already one process in the critical section, no other can jump in. Now if no process is executing in the critical section and some process wishes to enter, okay, and so now there is one more. This is kind of avoiding starvation, right? So what if that other process never gets a chance to execute? What? So this is what if this keeps on executing itself? The bounded waiting is basically to there is just a bounded limit on the number of times that a processor allowed. Okay, and then the third thing is basically bounded, right? Because we can have only have one process executing in this critical section. So all the it could happen that process P1 will always occupy the critical section. Then P2 and P3 would face starvation, right? Okay. This is nothing but unfortunately this solution. Okay, then there is an issue with the solution. Okay, so this is the critical section problem. However, we can make no assumptions concerning the related. At a given point, any kernel process may be active in the operating system, resulting in the data set admins list of open files. The list must be modified when a new file is opened or closed. If two processes or two open files simultaneously separate updates. For example, I have process P0 and P1 creating child process fork. Uh, yeah, so that is what Peter's solution, right? We defined some three things, right? That this solution is correct. We need to okay. There is no. There is the confusion. So the Peterson solution. Wait, there is something, some issue. Okay, so critical section. So we add a something. Yeah, so we do three things. These are basically called as Coffman's. Uh, so Coffman's conditions, right? Okay. So this is not these three. This is called. This was derived by a person called as Coffman. So this is called as Coffman's solution. So now, how to achieve this? All the three in when I have multi-processing system, right, or I have multiple processes being scheduled. So first solution is Peterson's algorithm. Now this algorithm will only work for two processes. So Peterson's algorithm is this is used to solve the critical section problem for two processes. If you have multiple processes, then this won't work. For two processes only. Okay, so now yeah, the problem is so what does it do? So let's understand the Peterson's algorithm. Like how did Peterson derive an algorithm for two processes? Okay, so for example, let's say if one process wants to enter the critical section, so if suppose this is the common resource that I'm trying to share, and I have two processes, so this is process say P1 wants to enter. If only one process wants to enter the critical section, since there is no other process right now, so this will go in the section immediately. If both want to enter, then the one who didn't set the turn last gets in. The turn variable ensures that the bounding waited by giving priority to the other process. So then I have okay. First is basically the moment P1 goes in, then I do something or lock. Basically I indicate a flag saying that there is someone in the critical section, right? Because if the mutual exclusion principle states that if a process is under the critical execution, then we need to wait. only one process can pass the while loop condition. Okay. Uh, let's see. Uh, so how does it achieve? Is by making the flag true, right? Now let's so let's how so what it does is, okay. This is for both processes. Okay, so the moment now see what is going to happen. So what if there is already a process present inside this? If there is already a process, then the new process that wants to enter should have to wait, right? So flag 1 equal to true. Uh, so I'm going to have two processes, right? So the process that wants to enter, what is going to do is it's going to make its flag 0, right? Going to make its flag 0 to be true, saying that I want to enter. So flag 1 is equal to true. Uh, okay, so I need to this the flag is basically for rotation, right? So I have two things, flag and turn as well. I guess by flag setting the flag equal to true. Uh, okay, so I also want to rotate the turning, right? I don't want one process to uh, keep on executing, right? So each process, what I'm going to do is I'm going to denote it by say some number. So this is say 1 and this is say process 2, right? I want to enter uh, both processes want to enter the section at the same time. So what does process uh, so for this is for process 1. So it sets its flag equal to so this is flag made true, saying that I want to go. Now then the what it does is it checks if its turn has come or not. So if its turn is 1, and so does process 2 as well, it will also make its flag go true, saying that I want to enter. Now both flags 1 and flag 2 both are true. Now turn is basically going to decide which is going to enter. So then first this checks if the turn is of 1, then this will enter the critical section. Okay. So process 0 checks. Now when this turn is made 1, or when the turn is of 1, now even process 2 will check, but since the turn does not match, then it will not be able to enter the critical section, right? So mutual exclusion is already achieved here. So by mutual exclusion, so okay, this is basically we are achieving mutual exclusion and bounded wait together itself, I guess. So that turn variable not only helps us to enable mutual exclusion, but it also makes bounded wait, right? That the turn will change. Uh, uh, But then the one thing that I'm not able to understand is how does it make sure that the other processor also gets the time. Think of uh, the other one is going to wait till the first one is going to finish. It's something like that. So I have two people, fly one and turn one. Oh, so based on turn. Oh, so this turn is basically indicating which is going to go. Okay. Now, if one is not interested, the other will proceed immediately, right? That I want to go. Now, no processes start because what happens is, uh, so if one enters, it is going to make the turn variable go to 2. So the earlier variable. Oh, okay, okay. Yeah. So there is. What is the difference between race around? So race around. Okay, let's go into. Uh, so whenever. Okay, so for process synchronization, you have two problems that occur. First is you can either uh, first is you might go into a race around, right? So every so different threads are access in the same block of code. The critical section is so the job of critical section is that part which has the shared resource. So race around is when you are having okay. I got this. So what if I'm having different processes, right? So I'm having P1, P2, P3. So I'm having P1, P2. These are different processes, right? But the problem in these processes uh, is that these processes are accessing the shared resource at a very good speed, right? These are accessing the shared resource rapidly. So what happens is we might get an incorrect value, or we are racing around. Like it's like a race, right? The one who is the faster will reach the resource. So that is what is happening in this racing. Now, when we do critical section is so critical section is basically um so critical section is we are trying to protect code block that accesses the shared. So what is, see if I have two processes and what if they are accessing a shared resource? So now there is a problem here, right? So that is nothing but it is basically to prevent race around. So it's basically to prevent the race around thing. So we don't want race around happen. That we don't want the process that reaches first to or the process that is fast that reaches and modifies. We want a proper sync between them to happen. Like even though that you are fast, don't change the value. So we want that syncing to happen. So for that synchronization, we define something called as Coffman's conditions, right? Or Coffman's, however you say. So for that reason itself, we have something called as Coffman conditions. So Coffman condition has three things, saying that if there is a shared resource that is accessing, only one resource, one process can access the shared resource at a time. Third is if the process has already accesses the shared resource, give the other process a chance to access it. The second is basically progress, right? So progress is basically no process should block other. So basically they shouldn't be blocking. So if P2 wants to access, so P1 shouldn't come and block it. This is basically fair mechanism. We need fair turn. This is avoiding starvation over here. This is making sure that proper races, no racing is happening here. So if one process is already accessing, the other has to wait. And this is basically where we are uh, not allowing blocking, right? One process not blocking the other. Okay, so then, so for two processes, for P1 and P2, if I want to access a shared resource, we came up across a solution that is called as Peterson's algorithm. So what does it do is, initially both P1 and P2 will say that we want to access the critical section. Now both P1 and P2 will be assigned a turn variable, right? So whosoever turn is there, and then there will be a turn checking mechanism here. So it will check the did P1 and P2 request for the section, and is it whose turn it is. If it's P1 term, then it will go inside. But then the problem is, what if it is always P1's term? So what it does is, this is going to, if P1 goes inside, then it is automatically going to assign the turn variable to P2's turn variable. Like the value of P1 is going to make and change the turns. Yeah, so what do we say? It changes the turns variable so that next time P2 can go and access. But if P2 is not interested, then it shouldn't give it the its turn should never come, right? So the flag checks if the process wants to come or not. The turn is for alteration, so that if one goes, then it changes it to two, so that two also goes, and this avoids that waiting, right? So we are doing bounded. And progress is if there is if P2 doesn't want, then it should never enter it in the first place itself, right? Okay. But then what is the drawback here? What are we doing? There is a drawback of Peterson's solution. So although it follows the Kaufman's principle, but then there is still something that you're going to work. So now, what's the issue? There is CPU wastage happening here. How is that wastage happening? Oh, okay. So what Peterson's algorithm does is, so I have two persons. Suppose you have two students, right? S1 and S2, and we both want to use the washroom. This is the shared resource. So first, we will both go to the professor and we'll say that we want to go to the washroom. Okay. So now what professor says, okay, S1 you go to the washroom. So S1 enters. But then S2 also wants to go to the washroom, right? So he'll stand outside. And he'll continuously keep on checking whether S1 has left or not. This continues is going to starve the cycle, right? So this is continuously checking over here. Wait, it's checking over here. It's polling like, okay, the moment you come out, I'll go in. So this is nothing but where we are going to waste the cycle. Yeah, and this is he's going to unnecessarily block for other threads, right? Because he's interested and he's already blocking it. So okay, so that is a problem, right? Oh, but so now when he's checking this for this checking to happen, CPU has to be notified, right? So what if there is other processes in the background that need scheduling? They won't be able to come. Oh, okay. It's continuously asking if it's empty or not, whether it's empty or not. So the CPU is gone now. So we have wasted CPU cycle again. The better way would be the better way would be if there is someone already in the washroom. We don't want the other process P1 to keep on polling, right? So what we do is, so if P1 is already inside, so what P2 does is it sleeps. The CPU is going to awakes the P2, and then it's notified that now you can enter. So we have uh, yeah, so we have reduced that what do you say, blocking mechanism, right? So this critical section problem can happen wherever we are having concurrency, right? So it can happen within the process, or it can happen when you are so basically this is a problem of concurrency, right? Although concurrency is good, you can do multiple tasks, but then the biggest problem of concurrency is how to overcome the critical section. That is a bigger headache. So uh, wherever we are achieving concurrency, so wherever we achieve this concurrency, we'll end up with the problem of critical section. This has to be carefully handled whenever you are doing any concurrent operations. So wherever there is a shared resource and there is a concurrent execution happening, uh, critical section will arise. So for multithreading to happen, yeah, for multithreading to happen, the language should support threading module, right? It should be able to happen, or you should have that threading feature in place. For example, there is a language called a JavaScript. So JavaScript is a single thread language, right? Uh, so for example, single threaded language like JavaScript. So JavaScript does not have multi-threading, right? Because it's a single thread language. You cannot create there is concurrency, but it is achieved in some other way. For example, Python in Java you have that thread pool, right? Thread pools. So this has that problem. Now Python has a threading module, but there are other ways as well to do concurrency. Swift again, the dispatch, because concurrency in Swift is achieved using threads, right? Although you have a new, yeah, concurrency in Swift again, thread dispatch. So again there is that critical section issue that is going to happen. So multi-threading depends upon the language and the feature. However, JavaScript has something called as event loop, uh, libu, that is a part of libu, right, using which it does. Okay. So then JavaScript, now this is a big advantage, right? Uh, because that critical thing, yeah, JavaScript will never have that classical critical section thing because there's no concurrent access, right? It's a single thread execution context. So we won't have semaphores and something else. It uses some other behavior, that is something called as event loop. It's important to know, although okay. The mutex locks now. Um, so this is basically so we discussed the software solution, right? So hardware based solution is basically, so there can be an hardware solution as well. So hardware solution is basically something. Okay, so to achieve, so the solution to critical section can be achieved in two ways. One is you achieve a hardware solution, the other is you achieve a software based solution. So either you could have a hardware or you could have a uh, what do you say? For example, you have Peterson's algorithm. This was the software. Then you have bakery algorithm again. So now this is at the user level. So mutex and semaphore. Remember we said that our operating system has two distinct uh, features, right? You are at the user level or you can be at the kernel level. But if I so whenever you are going to access an API, right? So preempt is when you are going to schedule, right? Do also preemptive. Remember, multitasking is when we are going to change, right? Is when processes are pushed out. The OS kernel, okay, but mutex and Well, there is a famous video of CPU. Why did it say that? Okay, wait. Something changed. So we haven't seen about memory yet. We'll see that. Then it'll make more sense. Oh, this is a good part. At this point, we should see this thing. Uh, this is yeah. It's why is it not? Yeah. So I guess yeah, this is a good point that we take a break, and we'll continue the next one. Uh, till that time, yeah. See you in the next one. Till that time, take care. Bye bye.